Hello, I am Katherine Blundell, Oxford Professor of Astrophysics and Gresham Professor of Astronomy, and I'm interested in recruiting students who share my love of the dynamic universe. I love things that change, I love things that explode, I love things that accelerate and change the way we think about how space evolves. If you're at all interested in this, then I reckon you might be rather interested in the projects that I'm offering this year. If we're going to study and investigate objects that change on human-friendly timescales, then we need a means of gathering the relevant astrophysical data. In order to do this, I set up the global JetWatch network of telescopes, observatories distributed in longitude around the globe, so that there is always at least one of them in darkness. Each observatory is equipped with a telescope, a spectrograph, and auxiliary cameras. And so we can gather data on phenomena that are changing. This is the top end of my telescope in Chile, looking out on the Scorpio constellation. This is the back end of that same telescope, demonstrating some of our sophisticated instrumentation. The Global JetWatch delivers time-lapse spectroscopy to elucidate studies on relativistic jets, accretion disks, and powerful outflows in microquasars and other compact objects such as white dwarf binaries and nova explosions. In recent years, I've become very interested, besides the above, in circumbinary orbits of matter, and particularly the circumstances under which they give rise to planets. Time-lapse spectroscopy is a powerful tool in the toolkit because it means that we can follow the dynamical evolution of something that is changing real time. And my experience is every time you look at a spectrum, it's different from how it was the night before. We have dynamical models, astrophysical models, that underpin our understanding and our investigation of the spectra, the data streams that we obtain. And it's enormously good fun to be able to confront our models with the new data as it comes in round the clock, night by night. If we only observe once per 24 hours, we miss out on the complete picture of what's changing. These two spectra here were taken of one of our targets 24 hours apart, and you can see that they have changed significantly and dramatically. We need to obtain the missing pieces of information so that we can accurately understand their full behaviour. Time-lapse spectroscopy enables us to elucidate all sorts of different behaviour. If we were to have insufficient temporal resolution or insufficient spectral resolution, then we would not be able to do the kind of investigations that I'm interested in pursuing. These two movies here at low spectral resolution are indistinguishable. Yet with fine spectral resolution, you see you have a totally different dynamical picture. Absolutely stationary with wavelength emission lines on the left-hand side arising from a circumbinary disk. On the right-hand side, Doppler shifting arising from a very simple binary orbit. I'm interested in the physics that underpins the spectacular phenomena that we study in the night sky. And frankly, that involves using all the tools in the toolkit: analytical expressions, simulations, observations, pertinent observations. And we can derive from a single spectrum of a microquasar the launch speed of the plasma that's ejected from the vicinity of the black hole and the angle at which the plasma is launched. Knowing the velocity vector means that we are well on the way to beginning to understand the detailed links between the cause and effect processes of accretion of matter towards a compact object like a black hole and the expulsion of matter, for example, in jets. I'm particularly interested in how different phenomena arise in terms of the eccentricity of the inner binary that is invariably at the heart of these exotic phenomena like microquasars, like nova explosions, and increasingly these days, like circumbinary orbits. Circumbinary orbits are thought to play an important role in not just preserving the eccentricity of the inner binary, here shown in white, but actually driving up the eccentricity of that system. And the interactions that you can get within these different dynamical phenomena are huge fun to study. We've got the data streams with which to do this. We have time-lapse spectroscopy and systems that may be simply modelled, yet may absolutely miss out on the full richness of astrophysical reality, are things that we really like to get our teeth stuck into. Not only do we do time-lapse spectroscopy, but we do simultaneous photometry as well. We have auxiliary cameras which help us do that. And this picture here shows you the main body of the optical tube assembly. This particular telescope is the one that I set up in rural southern India. Underneath the optical tube assembly, you can see a pair of red cameras. These cameras give us our simultaneous photometry. They are commensal cameras. These enable us to do very, very accurate spectrophotometry. They also enable us to search the light curves for the thousands of stars that are in their very wide fields of view and to look for interesting behaviour, such as bizarre and exotic transits that would arise in circumbinary systems, and so much more. If you're at all interested in this kind of work, then please do get in touch with me. Do drop me an email. Thank you very much.